Lecture 2. Types of energies within molecules. In this, we will have the subheadings: energy, energy separation, origin, that's where the energy comes from, and is this energy quantized or not? Let's start with electronic. The energy separation of the order of 10 to the minus 18 joules per molecule, or 600 kilojoules per molecule, per mole. And this comes from orbitals, and yes, it is quantized. Then we go to the vibrational energy, whose separation is 10 to the minus 19 joules per molecule, or 60 kilojoules per mole. And this comes from atom system. Is it quantized? Yes, it is quantized. We then go to rotational energy. The separation here is 10 to the minus 22, or 60 joules per mole. This comes from rotations about axes within a molecule. And yes, it is quantized. When we come to the translational energy, the separation is of the order of 10 to the minus 39 joules per molecule, or 6 times 10 to the minus 16 joules per mole. Translational energy is not quantized. It is linear. Further energies. Energy change resulting from interaction with an applied magnetic field, in bracket, less than vibrational and rotational. Then we also have transitions between energy levels due to orientation of spinning atomic nuclei, which gives rise to nuclear magnetic resonance, NMR. Then we have transitions due to electron orientations in substances with unpaired electrons, that's electron spin resonance. Let us look at this energy level diagram. Now, in this energy level diagram, you can see that the short lines here in black represent the rotational energy levels. Then the slightly longer ones, which should be blue, represent the vibrational energy levels, where that is V equals 0, V equals 1, V equals 2, and so on and so forth. Then the red lines, which are very far apart, represent the electronic energy levels, with the one at the bottom representing the ground electronic state, and that one representing the first electronic excited state. As we can see, the diagram represents the magnitude of the energies and their differences. Let's look at transitions between energy levels. If an atom or a molecule absorbs or emits, system moves from level E1 to E2, or vice versa. Associated frequency is given by delta E is equal to E2 minus E1, which is equal to h nu, where h is Planck's constant, nu is the frequency, or h nu bar c, where nu bar is frequency per centimeter, or hc over lambda, where lambda is the wavelength of the energy. Emission, delta E is equal to E1 minus E2, which is again equal to h nu, which is equal to h nu bar c, which is equal to hc over lambda, and that would be absorption. Here's an example. If delta E is equal to 0.01 kilojoules per mole for rotational transition, then nu would be equal to 15 times 10 to the 10 hertz, or cycles per second, and nu bar is equal to 5 per centimeter. From electromagnetic spectrum, this is in the microwave region. Regions of absorption. Vibrational transitions are observed in infrared region, whereas rotational transitions are in the microwave. Electronic transitions are observed in the visible and in the ultraviolet regions. Okay, let's start by looking at the pure rotational spectroscopy or microwave spectroscopy. This arises from rotational energy changes within the molecule. The molecule must have a permanent dipole moment for it to absorb in microwave. As it rotates, the changing dipole moment interacts with the oscillating electric field of the electromagnetic radiation, resulting in absorption or emission of energy. Consequently, homonuclear diatomics are inactive. Heteronuclear and polyatomic molecules are active. Let us look at a model system. That's a rigid rotor model of a diatomic molecule. Now, in this, M1 is one atom and M2 is the other. There we have the y-axis and the x-axis and the z-axis. If we look at the distance of separation of M1 and M2 as r, we can look at a situation where we have a center of mass here. Consequently, R1, that is from M1 to center of mass, is R1, and from M2 to the center of mass is R2. Let's look at moment of inertia I. Moment of inertia I about x-axis is 0, because during the change or the rotation about the x-axis, there is no change in dipole moment. However, moment of inertia about the other axis is given by I is equal to m1 r1 squared plus m2 r2 squared. Let's call that equation number 1. If r, the internuclear distance, is the sum of r1 and r2, then we can consider the moment of inertia m1 r1 to be equal to m2 r2. In short, the system is at equilibrium. This implies that we can look at r1 as being equal to m2 over, open bracket, m1 plus m2, close and close the second bracket, times r, and r2 would then be equal to m1 over, open bracket, m1 plus m2, close and close the outer bracket, r. So that those are the r1 and r2, which are the distances from m1 and m2 to the center of mass. Let's substitute this into equation 1, and we will get I is equal to m1 m2 over, open bracket, m1 plus m2, close and close the second bracket, into r squared. We can shorten this as I is equal to mu r squared, where mu is known as the reduced mass. R is the equilibrium internuclear distance because